So for the next hour, we will have 6 talks, so 10 minutes per talk. So so I will give a warning 2 minutes before you finish your talk, and then so just a reminder. So for the questions, please use the raise hand feature in the chat in the Zoom, and also so you could also put your question in the chat. So the first speaker is Matt Lister. So he will be talking about ngEHT, the Parsec-Scale Jet Kinematics. Please go ahead, Matt.
Okay. All right. Well, thanks. So I'm just going to give a brief overview of what's being learned from centimeter wave VLBI and how that's applicable to what ngEHT will be able to do at very small angular scales. So I'll be talking about results from the hobby survey, and this appeared on arXiv earlier this summer, and it's now in press and AppJ. And what we did was we looked at a very long-term coverage on nearly 500 radially loud AGN. These are primarily Blazars, where the jets are coming right at us. The timescales range from 2 to 25 years. So this dates back to the original origin of the VLBA. And the actual cadences of the observing are tailored to the individual sources, because some of these jets, they move very, very slowly on the sky, microarc seconds per year, while others move very fast, milliarc seconds per year. So you really have to have a range of cadences that monitor the motion. And the main takeaways for this talk are that we've seen evidence of acceleration and collimation at scales up to 100 parsec. That's downstream of the central engine. And interestingly, if we look at the launch directions of these bright features that emerge from the unresolved core and move downstream, those launch directions seem to change over time, with a few cases showing oscillatory behavior. So the takeaway here is that with microarc second movies from ngEHT, we're going to see some really exciting phenomena. So our current VLBA view of AGN jets, if you take a single epoch image of a jet, like a Blazar with the jets coming at us, you'll see individual features that move slowly on individual trajectories, and you're not seeing the whole jet here. These individual features only occupy a small portion of the whole jet cross-section. And because we have limited dynamic range, in order to see the full jet, currently we just have to stack. So over time, here is almost 21-year stack of data from about 25 years of data from this particular jet that shows you a nice conical outflow, whereas an individual epoch, you might not infer that at all. So this is a lesson for ngEHT. We're going to need short baselines, extremely high dynamic range imaging if we want to see the whole jet emission. So if we look at these jets over time, what we did was do Gaussian model fits the visibility data. And at 15 gigahertz, you can get down to about 0.2 milliarc seconds from the core. And at the distance of these jets, that's about 1 to 2 parsecs projected distance. And what we see over time is that for the most well-monitored jets that we had, the inner jet direction changes typically by 10 to 40 degrees. And there are some cases where you have very large changes up to 150, even 180 degrees on the sky. And again, this is exaggerated because the jets are coming at us. So any intrinsic change is going to be much smaller than this. It's just exaggerated because due to projection. An example of a source which has a large change in interjet position angle is this one right here. And here's the VLBA image. We can get much higher precision on the actual positions of the features close to the core. And we can see this particular feature is moving in a non-radial direction. So the core is down in here, and this is only 0.2 milliarc seconds away, but it's moving in this direction. And so the apparent jet position angle of this particular AGN seems to move from left to right over time. That's a 90-degree change, and that's shown here in this plot of position angle versus time. So there's numerous examples of this steady sort of rotation, and this is one way of getting that. In other jets, there is a different type of behavior where features will emerge at consistently increasing or decreasing position angles. So it's not a random process. Each new feature knows something about where the last feature was launched. Classic example is 3C273, where in the early 90s, features were coming out more towards the north, and then steadily new features would come out towards the south, and now we're starting to come back. So you can see here, this was a feature that emerged in 2002. This is our fitted trajectory, and then here's another one that's coming out in this direction. So this is this type of oscillatory behavior. It suggests there's some sort of precession-related instability near the jet launching site. And that's pretty exciting. Here's another example where we put the numbers here on the individual features that correspond to the rejection order. So the core is up here. This is about 20 parsecs projected. And you can see this feature emerged, and then feature 3 emerged, and then feature 4 emerged. And there's a steady progression towards the west here. And then feature 6 is now coming more to the east. And just another example showing you different epochs of how there's a progression of ejection launch trajectories. The other thing to notice is that there's an overall curved channel that the jet seems to know about, and that these individual features are only occupying a small portion of it. Now, for the oscillating ones, you can see we fit some periods to these. It's hard to claim any periodicity because of the fact that the periods are decades long, and our data set is only about 20 to 24 years maximum, and that's only on the best sampled sources. But you can see there's evidence of back and forth motion. The amplitudes vary. Here's a 4-degree amplitude. Here's a large one, 25 degrees. So I don't have a lot of time to get into the theory of this, but this could be some sort of related to the accretion disk. There's a launching site in the accretion disk that orbits. Could be the whole jet rotating, or maybe there's a magnetic field line that's anchored. It's also rotating. That's responsible for where the features are emerging. Or there could be external torque, say from a supermassive binary system. And this is a result that's going to come out on arXiv tomorrow. It is one of the Mojave sources, and we've identified, this was the OVRO program with Tony Reedhead and collaborators, a sinusoidal period. And this is a very long-term stable period, dates back actually almost to 1980. This is the OVRO data, which shows you almost 3 cycles of it. But the interesting thing here is we don't see any evolution in the interjet position angle. So all of these variations are happening very, very close to the core within about 0.3 milliarc seconds. So this is where ngEHT is going to really shine. So if this is a supermassive black hole system, we'd be able to image close in where these flux variations are happening and be able to see possibly these changes in position angle. So just to summarize, we do see this oscillatory behavior in the launch directions over time. And with ngEHT, we'll actually be able to see where those features are emerging. They're going to fade rapidly at 230 gigahertz, but then we can keep tracking them if we go to lower frequencies with the VLBA and other VLBI arrays. So the main questions here for ngEHT are, why and when do these major jet feature ejections occur? They seem to occur about once per year in most Blazar jets. We don't know why, what that time scale is relating to. And is that, are these oscillation periods connected to perhaps accretion disk rotation, supermassive black hole orbits, or helical plasma instability? So all of these be suggested mechanisms, but we really need ngEHT's resolution and movie capability to address them. And just if you're interested in the data and the movies, you can go to our website down in here. Okay, and I'll stop there and I'll take any questions.
Wonderful. So I think we have time for a couple of questions. Is there any raised hand?
This is Thomas. Hi.
Hi.
Matt, with regard to your previous source with this established periodicity of 700 days or so, any idea how bright that source is? I mean, the problem is that most of these jets have a rather steeper spectrum and tend to disappear at 1 millimeter. So what kind of sensitivity would we need?
Yeah, so this was a Tujansky source.
At 15, but at 230?
230, typically, I just did some recent spectral index back of the envelope you typically get around a -0.6 spectral index between 15 and 86 gigahertz. There's a spread to that, but this one would still be above, be below a Jansky, around 0.2, 0.3 Janskys, I would think.
Yeah, okay.
Millimeter.
So not terribly bright, but still doable.
Mm-hmm.
So any other questions?
There will be targets available for ngEHT at sort of the 0.1 to 0.3 Jansky level.
Okay. Are there any other question or? Oh, Avery, do you have a question?
Yeah, a quick one.
Yeah.
So Matt, this is fantastic. Of course, Mojave has been just an extraordinary project, and for people like me who don't touch the telescopes, an amazing resource. So thank you for that. You do take full polarization data, right? So I was wondering, looking forward to potential ngEHT requirement questions. Do you see a wiggle in polarization associated with this period? Is something like a coherent rotation measure mapping strongly motivated by this sort of science?
Yeah, the polarization is difficult due to blending very close to the core. So what typically the unresolved core feature is responsible for most of the polarization signal. But then what will happen is a new feature will emerge, and then you'll get a period where there's a blend where the polarization can actually drop in the case where the new feature has an orthogonal polarization. So you get beam depolarization essentially. So that's a problem when you're really, really close to the core. So we can't really say, oh, well, the new feature is ejected on this position angle, and we know what the position angle of the polarization is. So we can't really do that with centimeter VLBI, but with the angular resolution of ngEHT, it will be possible to do that. So that'll be very interesting because it will let you probe, for example, whether it's related to magnetic field lines, these different position angle ejections.
Right. Do you have any sense for what kind of resolution we would need in order to, I guess that's a hard question to answer without the ngEHT already observing. But yeah. So do you have any sense for, you must, if you see a dip, you must have a sense for how extended the polarization from the ejection is.
Yeah, I mean, the best constraints we can do are from current 43 and 86 gigahertz VLBI, where we can probe the brightness temperatures of the features that come out, just how compact they are. And it suggests you do need, tens of microarc seconds at sort of an upper limit. And then field of view, you would want at least 100 to 200 microarc seconds to get down into that launch region.
That sounds perfect. Thank you.
Yeah, killer app here.
Okay, thank you. So I think we should move on because we are running short of time. So our next speaker is Georgios Paraschos. Can you share a screen?
Yes, 1 second.
Yeah.
Okay.
Please go ahead.
Good. Okay, hello. My name is George Paraschos. I'm a PhD student at the Max Planck Institute for Radio Astronomy in Bonn. And today I give a talk on behalf of my collaborators presenting some of our results of a high resolution study of the core of 3C84 with millimeter VLBI. And I will also make a case why 3C84 should be observed with ngEHT. So before delving into the results, I thought of providing first some background information about this source. 3C84 has been observed over a multitude of frequencies over the years. Here I show some characteristic plots of how the source looks at 5 through 86 gigahertz from left to right. Notice the great detail at which we can resolve the source owing to its close proximity to us, which is about a parsec. The main components of the source are the bright VLBI core, visible in all frequencies, the component usually called C2, which is prominently displayed at the 43 GHz map, and as well as the most recently ejected component called C3, which is manifested as a bright knot in the south side. And also in the middle panel, the famous radio Astron map, which prominently displays the edge brightening of the jet in the initial 2 to 3 milliarcsecond from the core. A brief review of the main characteristics of 3C84. Over the last decades, it exhibited 3 major brightening events in the 60s, in the 90s, and in the early 2000s. The northern counterjet has been detected at 8, 22, and 43 GHz, and tentatively at 86 GHz as well. Free absorption from the circumnuclear torus has been proposed to obscure the counterjet emission. And remarkably, the jet brightening before the year 2000 to limb brightening after 2010, at least at 22 and 43 GHz. Regarding the kinematics, components move at 0.1 C near the jet base and accelerate to 0.3 to 0.5 C downstream. The jet follows an asymmetric mirrored S-shaped path with curved trajectories. The spectral index is inverted in the counterjet side of the jet, and the core exhibits a flat spectrum, whereas it steepens downstream. Circular polarization of 3% is detected in the core, as well as linear polarization of 2% at 86 GHz, which increases with frequency. And high energy gamma ray emission has been measured, but the correlation with a specific radio emitting region near the core has been lacking so far. In this context, some of the complex unexplained behavior can be traced back to the location of the black hole, which influences the possible interpretations of the core kinematics. In our recent work, we showed that the black hole is around 80 microarcseconds north of the VLBI core, which corresponds to around 400 to 1,500 Schwarzschild radii. And on the right, we display the spectral index maps at 1543 on the left and 4386 GHz on the right, which reveal a robust spectral index gradient in the north-south direction. With this in mind, let's move on to individual epochs. This is still work in progress, so some of the results are still preliminary. On the left, you can see 3C84 at 43 GHz from November 2010 to May 2021. The core region can be adequately described by a total of 5 components, which are identified in multiple epochs. A very interesting feature is the apparent ejection of the component Q5 in March of 2019, which seems to be moving almost perpendicularly to the milliarcsecond scale jet flow. On the right, we display 3C84 at 86 GHz at all available epochs spanning more than 2 decades. Here, 15 components are employed to describe the core region due to the smaller beam, which resolves more fine structure. The same elongation can be seen here as well in the latter epochs. Here we display the component trajectories, which we saw in the previous slide. The top 2 panels correspond to 43 and 86 GHz. On average, we find the components seem to move as a little bit slower at 86 GHz compared to 43 GHz, which can be explained by jet stratification, meaning that the 86 GHz observations trace a slower and fainter inner spine, whereas the 43 GHz, the outer faster moving sheath. And the third panel displays the 4 cross-identified components, which move with comparable speeds within the error budget. A byproduct of our analysis is the computation of the jet collimation profile at 3 frequencies, namely 15, 43, and 86 GHz, which reveals a frequency-dependent jet width. For this, we fitted a power law to the expanding region, and the result is displayed on the left. A clear trend is observed where the higher frequency flux envelopes the lower frequency one, and the power law index increases with decreasing frequency, possibly pointing again to transverse stratification. With the EHT and the ngEHT, we'll be able to test jet formation physics of 3C84 at an unprecedented scale. Here are some simulations of what we might observe. We'll be able to discriminate between possible black hole location scenarios, as shown with the red dots in each of the 3 panels, which denote possible black hole locations. This can be done via direct imaging, spectral index mapping at 4386 and 230 GHz, as well as with polarimetry. Our ongoing monitoring of 3C84 with the GMBA includes an epoch right after the EHT observations of next spring, meaning that we will be able to combine observations from both frequencies. With this combination of 86 and 230 GHz, we'll look at the core in such detail that presumably we'll be able to detect the existence or absence of a spectral index in the transfers to the jet flow structure. Shown here are some possible scenarios of what we might observe based on our simulations. If we are looking at a Blandford and Payne type launching, which is the left panel, which we expect a rather flat spectral index at the center, then a steepening in the south. If it's a stationary shock or a uniform disk, so the middle panel, we probably observed a rather flattish overall spectral index. If on the other hand, the black hole is located to the west, we expect to find a spectral index gradient in the east-west direction. In any case, the EHT plus GMBA beam will provide unprecedented resolution for spectral index mapping. And with that, I arrive at the conclusions. So in short, 3C84 is a nearby radio galaxy, making the prime target image the jet apex. The components move at low speeds, thus the Doppler effects are rather small. These ejected components in the nucleus seem to initially travel in a perpendicular direction. And based on the velocities, the jet appears stratified. Furthermore, the measured expansion profile is consistent with an expansion and recollimation due to pressure of the surrounding medium. 3C84 is a prime target for ngEHT observations. The next generation EHT will provide high spatial resolution of less than 30 Schwarzschild radii. The dense UV coverage should enable us to image details of the very complex radio galaxy. High sensitivity observations will also trace faint jet emission in the jet and counter-jet side. The physical nature of the inner observable is still an open question. Free emission and/or dust and even a torus are potential explanation, or perhaps even something else. With nearing time, VLBI at longer wavelengths, namely 3 and 7 millimeters, we will study the spectral index and determine the rotation measure.
2 minutes, 2 more minutes.
Yes, thank you. And finally, let me stress again that we have ongoing observations of 3C84 at 22 and 43 GHz with the EVN and 86 with the GMBA. Our proposals for 230 GHz observations with the EHT got scheduled, so it will be a great opportunity for new science. And with that, I arrived at the end of my talk and would be happy to field any questions.
Okay. Thank you very much. A very interesting talk. Any questions from the audience? I have a short one. So is the edge brightening feature of the jet, is that a persistent feature or you know, is time variable?
You mean the one that has been ejected in the last few epochs?
Yeah. And I mean, also on the larger scale.
Right now we're waiting for the GMBA observations from last April and the ones we had in October. So it'll be very interesting to see if we continue seeing this component there. In larger scales, I don't think it has had enough time to travel so that we can see it, let's say, at 15 GHz yet. Although we do have also observations at 22 GHz next week, actually. So perhaps we'll be able to see it there.
Okay, thank you. So any questions from the chat? No? Okay, thank you again. Let's move on. So the next speaker is Antonio Fuentes. Antonio, are you there?
Yeah, I'm here. I'm sharing my screen now.
Please share your screen. Okay.
Can you see my screen or hear me well?
Yes, please go ahead.
Okay. Okay, so hi everyone. I'm Antonio Fuentes, last year PhD student at the IA in Granada of Spain. And today I will present the results that we have obtained for 3C279 with the space BLBA emission radioastron, and how it compares to the recently published EHT results, and what can we expect from the ngEHT. So this work has been made possible thanks to a large number of collaborators that are listed here. And let me also note that these observations are part of one of the key science projects, the radioastron collaboration, was already published several results for different sources and many more to come. Okay, so let's focus now on 3C279 observations. So the source was observed on March 2014 at a frequency of 22 GHz and supported by a ground array of 23 different antennas across the globe, and whose location can be seen in the rightmost figure. So radioastron observed in full polarization mode. So apart from Stokes images, we have linear polarization images that I will show you in a minute. And as you can see in the leftmost figure, the ground array UV coverage is excellent. And on top of that, we have baselines to radioastron spanning up to 8 Earth diameters, which for this observing wavelength, 1 centimeter, corresponds to a maximum angular resolution of 27 microseconds. Okay, so here you can see on the rightmost figure the same epoch BLBA view Blazar program image at 43 GHz, and how it compares to our image, which is in the left figure, if we combine both with the same restoring beam, which is the BLBA view Blazar restoring beam. So okay, this is how it compares to the EHT 1 millimeter image published in 2020. So this is a 1-to-1 scale. And so I know that this adds nothing new, and we want to directly compare to the EHT image, taking advantage of radioastron and the high transversal angular resolution it provides. So let me show you a quick movie. So in this movie, I'm decreasing the beam size up to the actual resolution provided by the imaging algorithm. And then I'm changing the color scale, so the dimmer structure seen in the image is more clearly seen. So let me play it again, just one more time. Okay, here you go. So yeah, this is one of the representative images that we have obtained with radioastron, and all the results. Let me also note that all the results presented here were obtained using the EHT imaging library, which I think was used for the first time for these kind of observations, to my knowledge. And also thanks to radioastron and its coverage transversal to the jet propagation direction, we achieve similar angular resolution to the EHT, but with a much larger dynamic range, I think 2 orders of magnitudes larger than the EHT, which together with the larger observing wavelength enables us to capture and resolve all the extended emissions seen in the 43 GHz image. Okay, so while traditional clean field reigns in the centimeter and space BLBA domain, I'm showing here how well current RML methods, in particular EHT imaging, perform for these kind of observations. So on the left, you can see the image fit into the visibility amplitudes and phases. On the right, the fit into a selection of closure phases, log closure amplitudes, and polarimetric visibility phases. All of them including radioastron in the particular triangle, quadrangle, or baseline. And as you can see, the image I presented before fits the data remarkably well, I'd say. Okay, so let's see now how our image compares to the EHT image. So in the figure, I'm showing total intensity, our total intensity image twice. So with the EHT image overplotted as black contours on the right. So the images are aligned using the pixel with the highest flux. And we can see that the core structure is consistent between the two. The base is elongated and tilted. And the core position actually, the core position angle actually varies a bit among the different images reconstructed. So we acknowledge that some rotation during these 3 years apart from the two observations is possible. The southern component seen in the ngEHT image matches actually pretty well one of the 3 arms escaping the core that we are able to record. And of course, in addition, we are able to capture 2 large-scale helical filaments that bend and converge twice, extending up to 1 milliarsecond far from the core in the southwest direction. And we also have polarization, as I mentioned before. So on the right, I'm showing again the same total intensity image, but this time with EVPAs overplotted, whose size is proportional to the linearly polarized emission. So the source is externally polarized with a degree of polarization of about 10%. And the EVPAs follow the filament's propagation direction, which indicates that a strong toroidal component, there is a strong toroidal component of the helical magnetic field. Okay. So regarding the mechanism involved in the production of these helical filaments, we believe these are surface modes of Kelvin-Helmholtz instabilities, probably elliptical modes in competition to helical modes. And why Kelvin-Helmholtz? Well, because the ngEHT paper indicates that the jet no longer accelerates beyond the 0.1 milliseconds region within the far from the core. And therefore, the filaments that we see in our image grow in the kinetically dominated region, which then suggests that this is produced by Kelvin-Helmholtz instabilities and not other mechanisms as current-driven instabilities. So based on these assumptions and the estimated wavelength of the filaments that we derive from fitting of the filaments, we are able to derive some properties of the jet and the ambient medium. And of course, since we are using an RML method, each imaging library, we also did some hydroparameter exploration in the same fashion as in the ABT7 paper published in the form of a mini parameter survey. So as you can see in the images here are quite consistent, and most of the features are also quite robust, although we know that some changes in the core position angle and the secondary filament are present. Like, for example, the secondary filament might be brighter or in some images and weaker in some others. But in any case, all these images, I mean, all these images that you see here are a subset of those that large amount of images that we reconstructed in the survey. But this selection that you see here, they all fit the data almost equally well. Yeah. So finally, thank you. So finally, yeah, to conclude my presentation, so here is the summary. Yeah, we have image 3C279 and 22 gigahertz with a nominal resolution of 27 microseconds, thanks to radio aston and 23 run antennas. The elongated and tilted core structure is consistent with the ngEHT 1 millimeter image, and the ngEHT southern component matches one of the arms seen in the radio aston image. So images, our images show one bright filament and hints of the second filament forming a helical structure extending up to 1 millisecond far from the core. Polarization results show EVPAs aligned with the main filament, which indicates a strong toroidal magnetic field component, and the helical filamentary structure might be caused by Kelvin-Helmholtz instability. Thank you.
Thank you. Very interesting talk. Are there any questions? I don't see raised hand.
I have one. I don't see how to raise my hand.
Go ahead, Alan.
Okay, and Antonio, to have the surface instability, I think you need to have the pressure equilibrium between the jet and the external medium. And if that's correct, then can you predict what kind of Faraday rotation you might expect if, say, the medium has a temperature of 10 to the 8 kelvins? Have you thought about that?
Yeah, thanks, Alan. I'm afraid we haven't we haven't thought about that really, and I don't think I can give you an answer actually right now about that.
Okay, I mean, it might be worth doing a back of the envelope calculation.
Okay, thank you.
Okay, thank you. I have a very quick one. So I recall that the larger scale, like on several mid arc seconds, the jet also shows like some kind of rotation. So can this ngEHT image and the radio astronaut image is not simultaneous, right? So it's like a few years apart. Can they the ngEHT image corresponding to one the other how to say part of the jet or one of the three features? How can you be certain that it's corresponding to which one of the three?
That's a very good question, Rusen. Yeah, so actually, yeah. So we so regarding the jet base, we know that there might be some rotation of the jet base. And regarding the southern component, actually we are attempting to say that this is the same, it's matching that arm that we see there, but we don't have any clue apart from the fact that it actually coincides with this arm here. So it might be that it's actually rotating and the southern component corresponds to a different one, maybe the left arm, which is the brighter one, and the one that shows the most bright filament. And actually, what we're seeing is a rotation of that component, and that's a very good question actually. And it's a possibility.
Yeah, thanks a lot. So let's move on because we are running short of time. So our next speaker is Aishwarya.
Yes.
Yeah. Okay. Yeah. Please share your screen and.
One.
Okay, the origin of black hole jets. Okay, please go ahead.
Yes. So first of all, hello everybody, and I would like to introduce myself. I am myself Aishwarya S, and I'm still a bachelor student. So this is a short. Probably you would all be knowing about this already, but I like physics, and this is what. With my limited knowledge, I have tried to make this presentation, and correct me if I go wrong anywhere. So my topic is the origin of jets. And what are black hole jets? So we know that every galaxies have one supermassive black hole, and these black holes have so much of gravitational force, and how did the jets come from there was a great mystery, because this has an enormous amount of gravitational force to pull even the lights couldn't escape from its gravitational force. And how could the jets be formed, and how these black holes power plasma jets? And this was one of the most mysterious thing which we could see. And then so we know that a black hole spins, and that is the main thing for creating jets. That is what we have thought so far. And the magnetic field at the poles of the black hole becomes coiled, and this is the reason why there's the formation of jets. And for this, there are like two famous energy extraction schemes which were made, and one was the Penrose process. The Penrose process told that it mainly dealt with the conservation of momentum rather than magnetism, and it also told that the rotational energy of the black hole is located not inside the event horizon but in the region outside known as ergosphere, and ergo means energy. So Penrose told us that if any object broke in the ergosphere, a part of it will be absorbed by the black hole and other part of it would be thrown away. And this was what the Penrose rule. And the other process was the Blandford-Zanagic process, which is very important right now. And this is what we had, I think it was proved in the recent image by the ngEHT of the M87 black hole. So this Blandford-Zanagic discovered that a process by which spinning black hole can transfer rotational energy to plasma. So here there's a bend of magnetic field. The space-time is curved and the magnetic fields coil into a helical form near the poles. And here there's a synchrotron radiation and the magnetic field is very high in this place. And that's when it emits the electrons and positrons far away at the speed of almost at the speed of light. And what could be the power of the jet? So the power of the jet is determined by two main things. One is the magnetic flux of the black hole surrounding the black hole and the spin. So here is a small simulation where we can see that the magnetic field lines are bending and coiling near the ends, and it powers the black hole jets in the poles. So we can see the coiling of the magnetic field near the black hole in this image. And this was the latest image taken by the ngEHT. This was the previous image which was taken, and here we can see that the lines are linearly polarized and the electric vectors are orthogonal to the magnetic field. So this was the image which told that the Blandford-Zanagic process, which was just a theory till then, is a reality after the image released by the ngEHT. And like previously, which I told, the power of a black hole. So this power, there's a limit to the power which black hole can be emitted. And that limit is known as MAD model, that is magnetically arrested disk. Here we can see that there's a strong and coherent magnetic fields in the disk and yet permit gas to accelerate. So we can see in this image that there is an accretion disk, and there is a necessity of having an accretion disk because it squeezes the magnetic lines near it, and these magnetic lines always want to escape through it doesn't want to stay near the black hole but to escape. And this is one of the reasons for the formation of the jets. And without the pressure from the accretion disk, this was kind of not really possible because the magnetic field would escape. And the same model is nothing but the weak and turbulent magnetic field in the accretion disk. So till now, the MAD model has been, in the recent observation, it has supported the MAD model. Recently, the scientists spotted the jets and they have even seen the jets from any other black hole and came into the conclusion that the mass or the mass of the black hole never really mattered to the jet which was emitted from it, and it closely resembled each other. That is, even the smaller jets coming from a smaller black hole could have a jet equal to a bigger black hole. So this is my presentation. Any questions?
Okay, thank you. Are there any questions? So I don't see a raised hand. So thank you again. So I think we can move on. So the next speaker will be Annie Baczko. Hey, Annie, nice to see you. Yeah, so please go ahead. Oh, sorry, this is not your screen.
Sharing screen.
So I think that Aishwarya may need to
One
Stop
second.
sharing, and then Annie can share, I guess. Can you stop sharing?
Yeah, once.
Yeah. Can you try now? Ah, yes. I see.
I hope you see my screen now.
Yes, but I think the voice is a little bit weak. Can you speak loud?
I turn it up. This way? Oh, no.
Your audio is very distorted.
Oh, no.
Anne, du bist total übersteuert. Versuch mal weiter wegzusprechen.
Ich bin schon weit weg.
This is better.
Ist es besser?
Ja.
Yeah.
Okay.
Go ahead. Very good.
Yeah, the screen.
Good.
Now it's better. Yeah. Okay. Okay. Please go ahead.
Good. Then I go now. So I want to also talk about jets, especially give a short overview on jet collimation in AGN overall, and raising some problems that are just arising. So I will give first a short introduction on what I want to talk about, then give an overview on jet collimation overall, to go to my special source of interest, NGC 1052, summarizing, and finally presenting some future projects. So the ngEHT was most about imaging the shadow of the black hole. So you see here the very nice image of M87. But M87 does not only have a black hole, it also has a jet. That it's especially one of the first sources where a jet was detected even in the optical. So what's interesting about jets? We can study the formation and the collimation jets. How are jets coming into existence by measuring the width of the jets, which we can do in radio astronomy with radio interferometers. So here, as you see the jet collimation profile of M87, I think that most of you already know about that, where we find when going from the black hole towards further outwards, we find a parabolic expansion going to a conical expansion with a change in M87 of around 10 to the 5 Schwarzschild radii. We can now have a look at other sources. For example, NGC 315 is also very nice, interesting source that shows at lower radio frequencies a double-sided jet that cannot be detected at the higher frequencies anymore. And we also see here a change from a parabolic to a conical expansion profile. But now the change is much closer to the black hole, below 10 to the 4 Schwarzschild radii. And now the question is, what is the reason for that? How can we explain these different scales of change from a parabolic to a conical, and why do we have a change from a parabolic to a conical change? There are a number of explanations for that. There might be a confinement from a thick accretion disk, especially the disk wind may play an important role in that. There might be some other kind of change in the external pressure profile in comparison to the jet, which also might trigger a change of the collimation profile. A very good explanation that is used very often also is that we have a change of the internal energy structure of the jets at this point, so changing from the magnetically to a kinetically dominated jet. Hence, when we are looking being in the parabolic region, we are in the acceleration phase of the jet, whereas starting in the case of NGC 315, at somewhere between 10 to the 3 and 10 to the 4 Schwarzschild radii, we are going into a freely expanding jet. There are many more examples where we see exactly that, a change from parabolic to conical expansion. And that is somewhere between 10 to the 4 and 10 to the 6 Schwarzschild radii. So we get a simple picture where we have now our black hole with accretion disk, and assume that we have the acceleration and collimation zone where we have a parabolic expansion of the jet going to a freely expanding jet where we find a conical. And this is these findings are perfectly in agreement, assuming a change from magnetically dominated to particle dominated jet. So in principle, we could think we are fine. We have an idea on how to explain what we observe. But as it is with experimental physics, we have some exceptions. So we cannot explain this cannot explain all sources with this model. So we already saw some nice images of 3C84. I want to emphasize here especially the collimation in the innermost region, which is not parabolic, but we find here a very more or less cylindrical collimation profile that has a polar index of around 0.2. We have a edge-brightened structure similar to what we see in M87, and a very wide jet base and a very wide intrinsic opening angle. This is not perfectly in agreement, assuming simply magnetic acceleration. We might have to add some confinement to an external pressure gradient. Another source where we can observe something similar, especially this edge brightening structure when going to ngEHT images or ngEHT wavelengths, is Centaurus A, where we also can test the width of the jet in the collimation profile, which is with an index of 0.33, neither parabolic nor cylindrical, so something in between. Another source that most of you, I think, know is also Cygnus A, which is one of the very few sources where we can study the collimation in a double-sided jet. So we can study the collimation profile when we have the black hole here at 0 into both directions, finding some small differences, and especially a very wide jet base and large initial opening angle. So what do we have now? We had M87 that that has a change from parabolic to conical, including many other sources. We saw 3C84, Centaurus A, Cygnus A, which show not really a parabolic expansion. So as last source, I like to present some of my own results on NGC 1052, which is also a double-sided jet source that is quite small in the radius, so with 3 kiloparsec size. It is core-dominated. It is close by, has a black hole mass of 10 to the 8 solar masses. And I will especially look at a multi-frequency data set taken with the real BA in the global array between 1.5 and 43 gigahertz. Here you see the multi-frequency data, or one part of this multi-frequency data set. When we go from low frequency to high frequency, there's an emission gap between both jets. And this gets smaller with increasing frequency as it is due to free absorption in a circumnuclear torus. This is a very straight jet. We don't see any edge brightening here. And going to the collimation, I have the possibility to really study here now the collimation for both jets. We see here on the left side
Sorry.
Yeah.
2 minutes left.
Okay, thanks. The eastern jet, the eastern approaching jet, and the western receding jet, and there are especially many different deviations from broken power law fit, which is nearly cylindrical, close to the black hole, and nearly conical outside of the black hole. and the jet is, in the Western jet, the receding jet is much wider. More interesting, and especially removing the impact of the outer wider jet at lower frequencies. You can see here the higher frequency, 15 to 43 gigahertz stacked images, resulting in again nearly cylindrical collimation up to 10 to the 4 Schwarzschild radii and a conical expansion further out. Especially there are differences.
It's frozen. I'm not animation.
Oh.
Okay. I'm merging 1.4 gigahertz image.
Oh, sorry. Where is? Maybe I just turn off my video. Maybe it helps. Something changing?
No. Actually, no. But I mean, time is up. So
yeah.
So the session will be closed soon. So I guess we can discuss in the Slack channel.
Yes. I think I tried to put on the presentation somewhere.
Yeah. So sorry, I think we have to move on.
Yeah, sorry.
So the last speaker is Alok Gupta. Alok, are you there? Okay. Okay. Yeah. Please go ahead. Are you? So you are sorry. You are muted. Okay.
Hello. Can you hear me?
Yeah.
Okay. Fine. Okay. So I am Alok Gupta from Nainital, India. I thank organizers for giving me an opportunity to give this talk. So I cannot change my slides. Okay. So what are the outstanding problems in Blazars? So first one is the finding intrinsic and extrinsic parts of radio emission. So these are the problems which I think where ngEHT collaboration can do important contribution. Second is getting densely sampled multi-wavelength data on intraday time scale and understand dominant emission mechanism in different electromagnetic bands, which is not well understood yet, and simultaneous multi-wavelength variability on diverse time scales, where data is missing in large frequency range, and QPO in different EM bands. Can we search for simultaneous QPO in multi-wavelength data on IDB time scales, which is not yet found, and emission model which can explain QPO on diverse time scale for single and or multiple EM bands, which is not yet developed. So radio emission is basically mixture of intrinsic as well as extrinsic mechanism. Extrinsic mechanism is the interstellar scintillation. So the main challenge is to find out how much portion of the variability is intrinsic to the source and how much is the extrinsic to the source. Here I will just show you two examples. This is a very famous old paper in 1991 where authors have claimed correlated optical and radio variability, where they show that this variability nature is basically intrinsic to the source. But if you see this right figure, here you can see correlation with 2.8 centimeter with 6 centimeter and 2.8 centimeter with 11 centimeters. And we can see it is not peaking at the zero line. It means there is some contribution, mixed contribution of intrinsic as well as extrinsic mechanism, which is not equal in the different energy band, different frequencies. In a typical Blazar light curve, we can expect these type of features: stable flux, decline flux, QPO, and flares. So there is a very nice observation where there are three continuous pointing by XMM Newton for this Blazar PKS 2155-304, where you can see this 1A where the flux is stable, and 1B and 3A where the flux is declining, and 2 where a hint of QPO was detected, and there is a flaring event in 1C and 3B. So getting such a good time resolution data in radio and gamma ray bands are still difficult, but EHT or ngEHT can provide such time resolution data in radio bands, and upcoming CTA can provide in very high energy gamma ray band. If we can get similar time resolution data, it will be possible for multi-wavelength observation campaign data to look for correlation in different EM bands on intraday time scales and understand the emission mechanism. This is the case of multi-wavelength cross-correlated variability. This is the famous source 3C454.3. Here you can see this is the gamma ray light curve with 1 day time binning, and this is X-ray, and this is the polarization. This is optical band, and this is infrared band, and this is radio frequencies: 4.8, 8, 14.5, 22, and 36.8 gigahertz. So a strong flare seen in the gamma ray, X-ray, and optical NIR during 2009, December 3 to 12. This is the flare, a strong flare. Emission in optical NIR bands rose more gradually than gamma ray and X-ray rays. X-rays, though all are peaked nearly at the same time, and optical polarization showed dramatic change during flare. So here it is anti-correlation. When the flux, the flare is there, the polarization is low and polarization angle is low. And when the flux is low, then polarization is high and the polarization angle is also high. And this combination of behavior appears to be unique. And here you can see that most sparse sampling is in the radio band, which we can expect from EHT. Filling the gap in SAD, this is the SAD of 3C279, where you can see large frequency range, simultaneous data are missing. So ngEHT/EHT can fill significant gap in radio frequencies, and hard X-rays, approximately up to 500 keV, needs to find the high energy tail of synchrotron part of SAD, which is not yet well understood. In many Blazar where we expect, especially in TED emitting Blazar, where we expect this high energy part of synchrotron SAD is lying in the very high energy hard X-rays, and lower energy part of IC SSC part of SAD, and VHE gamma rays, say up to 100 TeV, is also needed to fully understand the SEDs. So for QPO in Blazars, so there are three possible model. Accretion disk-based model, where one can expect a prominent hotspot on the rotating disk, which has ability to explain the QPO on time scale, intraday time scale. And this is a helical jet structure model, which has ability, I can say, to explain the QPO on IDV as well as STV and even long time scale. And this is a model which is a binary black hole model, which can explain the QPO on longer time scale. In many cases, when the QPO is detected on the long time scale, people use binary black hole model. So, but QPO reported in literature before 2008. Here I have just mentioned few papers, and QPO reported in AGN since 2008. So here I have mentioned 5 papers. You can see one in AJ, one in Nature, one is monthly notices, and here one in APJ and one in Nature. But later QPO detection in all these papers were either found wrong or statistically not significant. So search for QPO in AGN should be done very carefully by using multiple techniques. So sorry, this is Alok, yes, I will quickly finish. So
Okay,
this is,
so the room will be closed in 2 minutes. I
will
think.
finish. So this is the best example of QPO so far detected. This is the narrow line C41 galaxy, where QPO is detected on 1 hour time scale. It is an XMM mutant data, and so there are we have detected several QPOs on different time scales. So I will just quickly show one result, which is on 4.6 hours in PKS 2155, and where we have used multiple methods. So there are these are some other examples where we have got QPO in 2 EM bands. So this is the X-ray XMM Newton light curve. So we visually found there is a QPO. Then we did a structure function, MHAOV, PSD, data folding, and wavelet, and we got 4.6 hours QPO and with 3.8 cycle. And we used black hole mass estimation method, and we detected black hole mass for this source is 3.29 into 10 to the power 7 solar mass for non-rotating black hole, and 2.09 into 10 to the power 8 solar mass for maximally rotating black hole. And we explained this QPO finding with accretion test as well as helical jet model. So I will stop here. So in the present days of multi-wavelength astronomy, blazars are about one of the most interesting objects. ngEHT/EHT can provide high time resolution radio data, which can be very useful to understand radio emission mechanism at the shortest possible time scale. It will also contribute in understanding the complicated emission mechanism of blazars. A more generalized radio loud emission model can be developed, which may explain variety of variability features and QPOs. Thanks.
Thank you. Perfect. So I don't think we have time for questions. So so we can discuss questions in the either in the chat or in the Slack channel. So thanks for all the speakers of this session. So let's have a break. Is that correct, Avery?